When people hear the word supernova, they usually imagine a gigantic explosion filling space like a fireball, something with a clear size, a visible edge, and a single moment of destruction. But that picture is misleading. A supernova is not a single object, and it does not have one fixed size. It is a process that unfolds across time, space, and multiple physical stages, each with a different scale. Asking how big a supernova is forces us to confront what big even means in astrophysics. At the moment of collapse, the core of a massive star can be no larger than a city, yet it contains more mass than the Sun. Seconds later, a shockwave tears through the star at thousands of kilometers per second. Hours later, light from the explosion begins to outshine entire galaxies. Years later, the expanding debris forms a nebula dozens of light years across. Each of these stages is part of the same event, yet their sizes differ by factors of trillions. A supernova does not explode outward, like a bomb in empty space. It begins deep inside a star, driven by gravity, nuclear physics, and extreme pressure. The visible explosion is only the surface response to processes happening far below, in regions smaller than planets but denser than atomic nuclei. What we eventually see is not the explosion itself, but the aftermath spreading outward over centuries. So when we ask how big a supernova really is, we are not asking for a number. We are asking which phase we are measuring, which definition of size we are using, and which moment in time we are observing. The answer changes depending on whether we are talking about the collapsing core, the expanding shockwave, the light it emits, or the remnant it leaves behind. In this video, we will carefully unpack each of these stages, compare their true scales, and separate what is physically real from what is commonly imagined. No exaggeration, no shortcuts, just the actual size of a supernova, explained slowly. If this kind of slow, calm explanation helps you unwind, you can subscribe to Theories Before Sleep and let the universe keep you company. When a supernova begins, nothing about it is large in the way people imagine. There is no expanding sphere of fire, no visible blast wave racing through space, no sudden growth to stellar proportions. The beginning of a supernova is defined by collapse, not expansion, and the physical scale involved at this stage is shockingly small compared to the star that is about to die. A massive star spends millions of years holding itself up against gravity by fusing lighter elements into heavier ones. As long as fusion releases energy, the outward pressure balances the inward pull of gravity. But this balance is fragile. It depends entirely on the star's ability to extract energy from nuclear reactions. Once the core fills with iron, that ability disappears. Iron fusion consumes energy instead of releasing it. At that moment, the star does not explode. It loses support. The core, which may contain more mass than the Sun, is suddenly unsupported and begins to fall inward under its own gravity. This collapse happens extraordinarily fast. In less than a second, the core shrinks from a size comparable to Earth down to something closer to a large city. We are talking about a radius of roughly 10 to 20 kilometers. That is smaller than many metropolitan areas on Earth, yet it contains up to 1.5 times the mass of the Sun. This is one of the most extreme density transitions that occurs naturally in the universe. Matter that was once arranged in atoms is crushed so violently that electrons are forced into protons, creating neutrons. The core becomes a neutron-dominated object, and the density rises to values comparable to atomic nuclei. A teaspoon of this material would weigh billions of tons. Yet despite this unimaginable density, The physical size of the core remains incredibly small. At this stage, if you were to ask how big is the supernova, the honest answer would be that it is smaller than a city. The process that will eventually be visible across galaxies begins in a region that would fit comfortably inside a human country. Nothing about this scale feels explosive or grand. It is compact, violent, and inward moving. As the core collapses, it reaches a point where further compression becomes impossible. The neutrons themselves resist being packed any closer together due to quantum mechanical pressure. When this resistance suddenly halts the collapse, the inner core rebounds. This rebound generates a shockwave that begins moving outward. But even now, the scale is still small. The shockwave originates at a radius of tens of kilometers and must travel through the rest of the star, which may be millions of kilometers across. Initially, this shockwave is weak. In fact, early models showed that it should stall completely, losing energy as it rips apart atomic nuclei and fights against the enormous gravity of the star. This was a major puzzle in astrophysics for decades. How does a supernova actually manage to explode? The answer involves neutrinos, merely massless particles produced in enormous quantities during the collapse. In the first few seconds, the collapsing core releases more energy in neutrinos than the Sun will emit in its entire lifetime. These neutrinos stream outward in all directions, passing through the star almost unhindered. A small fraction of them deposit energy into the surrounding material, reviving the stalled shockwave and allowing it to continue outward. At this moment, the size of the active supernova region is still tiny by astronomical standards. The shockwave is only hundreds of kilometers from the center. The core itself remains roughly 20 kilometers in radius, yet the energy involved is already staggering. The total energy released in the collapse is around 10 joules, but nearly all of it escapes as neutrinos, not light or kinetic motion. This is an important correction to popular imagery. The dramatic explosion we associate with a supernova represents only a small fraction of the total energy budget. The true violence of the event is mostly invisible and confined to a compact region near the core. The part that eventually lights up the sky is, energetically speaking, a byproduct. As the shockwave finally gains strength and begins moving outward through the star's layers, it is still navigating an environment vastly larger than itself. The star's outer envelope can extend millions or tens of millions of kilometers from the core. The shockwave takes hours to reach the surface. During this time, the supernova is still not visually detectable from afar. The star is already doomed, but the signal has not yet escaped. Here again, the concept of size becomes slippery. The supernova exists as a process rather than a structure. Its most decisive phase occurs deep inside the star, on scales smaller than planets. The star itself has not yet changed its appearance. From the outside, it still looks like a normal massive star. When the shockwave finally reaches the surface, a burst of light known as shock breakout occurs. This can release an enormous amount of radiation in a short time, briefly making the star visible across vast distances. But even then, the physical region producing the light is a thin shell near the surface. The core remains tiny, dense, and largely hidden. So during the entire core collapse phase, which determines whether a supernova happens at all, the characteristic size is measured in kilometers, not light years. This phase decides the fate of the star, the creation of a neutron star or black hole, and the initiation of the explosion. Everything that follows depends on what happens in this minuscule region. This creates a striking mismatch between cause and effect. The cause is compact and localized. The effect eventually becomes enormous and far-reaching, but the initial scale never grows to match the later consequences. The supernova does not begin large and become visible. It begins small and becomes influential. Another misconception worth correcting is the idea that the entire star explodes simultaneously. In reality, different layers respond at different times. The core collapses first. The shockwave forms and moves outward. The outer layers are only ejected much later. At no point does the star exist as a single expanding sphere in the way a bomb does. From a physical standpoint, the most real supernova is the one happening deep inside the star, where matter is being crushed, transformed, and rebounded under extreme conditions. That supernova is tiny. It is dense. It is violent in ways that are difficult to visualize, but it is not large. If we were forced to assign a size to the supernova at this stage, we would be describing the size of the collapsed core and the immediate shock region. That size is comparable to a small moon or a city-sized object, depending on the exact phase. It is a reminder that astronomical importance does not require astronomical dimensions. This also explains why supernova physics is so challenging to model. The relevant processes involve nuclear forces, quantum mechanics, neutrino interactions, and relativistic gravity, all operating in a region smaller than a terrestrial country. Yet the outcome determines the chemical evolution of galaxies and the formation of compact objects across the universe. So, when we talk about how big a supernova really is, the first honest answer is deeply unintuitive. At its most critical moment, when the star's fate is sealed, a supernova is one of the smallest large-scale events in astrophysics. It is the ultimate example of how scale and significance can diverge completely. In the next stage, this compact event will begin to leave the confines of the star and grow outward into something that truly becomes large. But that growth is a consequence, not the origin. The heart of the supernova, the part that decides everything, never becomes big at all. As the shock finally forces its way outward, and the star's outer layers begin to respond, the scale of what we call a supernova starts to change. But not in the way most people expect. The growth is not sudden, and it is not uniform. Instead, size emerges gradually, almost reluctantly, as the consequences of the core's collapse propagate through material that was already there. The star does not suddenly become bigger. It becomes unbound. Once the shockwave has enough energy to overcome gravity, the outer layers of the star are no longer held in place. They are accelerated outward, but at speeds that are fast by stellar standards, not explosive in the everyday sense. Typical ejection velocities range from several thousand to tens of thousands of kilometers per second. That sounds extreme, yet even at these speeds, it takes hours to days for the expanding material to traverse distances comparable to the original size of the star. During this phase, the physical size of the supernova is best described not as a single object, but as a rapidly changing volume of expanding gas. The star's radius might have been tens or hundreds of millions of kilometers before collapse. As the envelope begins to expand, that radius grows, but it does so unevenly, shaped by the star's original structure, rotation, and composition. Some regions move faster than others. Some directions carry more mass. The expansion is messy, asymmetric, and complex. At this point, light finally begins to dominate what we perceive. The shock-heated material emits radiation across a wide range of wavelengths. For a brief time, the supernova can outshine the entire galaxy in which it resides. This dramatic increase in brightness often leads to the assumption that the supernova itself has suddenly become enormous. In reality, the brightness is not a reliable indicator of physical size. A relatively thin shell of hot gas can emit an extraordinary amount of light without occupying a large volume. Here, size becomes context dependent. If we define size as the region emitting visible light, then the supernova may appear to span a distance comparable to the original star, or slightly larger. If we define size as the region of material moving outward, then the scale continues to grow over days and weeks. If we define size as the region causally affected by the explosion, the scale is still expanding but remains tightly linked to the original star. What complicates matters further is that the expansion does not stop when the star's material leaves the stellar radius. The ejected gas continues moving outward into interstellar space, carrying momentum and energy with it. There is no clear boundary where the supernova ends and normal space begins. Instead, there is a gradual thinning of material as it spreads out. In the first few weeks, the expanding ejecta may reach distances measured in billions of kilometers. This is already larger than the orbits of many planets, yet still small compared to the distances between stars. The supernova is now undeniably large in a human sense, but astronomically speaking, it remains a local event confined to the immediate neighborhood of its former star. As time passes, the expansion continues. Months turn into years. The material cools, recombines, and begins interacting with the surrounding interstellar medium. Shock fronts form at the boundary between the fast-moving ejecta and the slower diffuse gas between stars. These interactions generate new radiation, particularly in radio and X-ray wavelengths, revealing structures that were invisible earlier. This is where the notion of size becomes particularly misleading. The supernova remnant, the long-lived structure produced by the explosion, can eventually span tens of light years. Famous remnants like the Crab Nebula or Cassiopeia fall into this category. When we see images of these remnants, glowing filaments stretching across vast regions of space, it is tempting to think that the original supernova was that large, but this is a retrospective illusion. The remnant's size reflects centuries or millennia of expansion, not the instantaneous scale of the explosion itself. The material has had time to travel enormous distances at high speed. The supernova did not begin at that size. It grew into it slowly, driven by inertia rather than ongoing energy release. This distinction matters because it highlights how size accumulates in astrophysical processes. Large structures are often the result of sustained motion over long periods, not sudden creation. The supernova provides a burst of energy that sets material in motion, but once that initial impulse is delivered, the subsequent growth is passive. The universe does not keep injecting energy to make the supernova larger. It simply allows the ejecta to coast. Another subtlety emerges when we consider different wavelengths of observation. In optical light, the visible supernova may appear relatively compact, limited to the brightest regions. In radio wavelengths, the remnant can appear much larger, tracing shock-accelerated particles far from the center. In X-rays, hot plasma outlines yet another structure. Each of these views suggests a different size, depending on what physical process we are tracing. There is no single correct size, only contextually useful ones. This challenges the intuitive desire to assign a single number. Unlike a planet or a star, a supernova is not a stable object with a well-defined boundary. It is a dynamic event that changes its spatial extent continuously. The expansion also slows over time. As the ejecta plow into surrounding gas, they lose momentum, the shock weakens. Eventually, the remnant merges with the interstellar medium, losing its distinct identity. At that point, asking how big the supernova is becomes meaningless because there is no longer a clear separation between what was ejected and what was already there. This fading of boundaries reinforces an important idea. The size of a supernova is not only time-dependent, but temporary. The explosion creates structure, but that structure dissolves. Over tens of thousands of years, the enriched material becomes part of the galaxy's general gas reservoir, indistinguishable from other sources of heavy elements. Even at its largest visible extent, the supernova remnant remains small compared to galactic scales. A remnant spanning 50 light-years is enormous by stellar standards, yet it is still a tiny feature within a galaxy that may be hundreds of thousands of light-years across. The supernova's influence is profound, but its footprint remains localized. This highlights a recurring theme in astrophysics. Influence and size are not proportional. A supernova can reshape its environment chemically and dynamically without ever becoming a dominant structure in the galaxy. Its power lies in the energy it injects and the elements it disperses, not in the space it occupies. It is also worth noting that not all supernovae leave behind prominent remnants. Some explode in environments with very low surrounding gas density, allowing the ejecta to disperse more quickly and quietly. In such cases, the remnant may never develop a bright extended structure. The supernova still occurred. Its size still evolved, but its visible legacy is faint or transient. All of this complicates the simple question of size. At any given moment, the supernova occupies a region defined by physical motion, radiation, and interaction. Those regions overlap but are not identical. The event resists being pinned down to a single scale. If we step back, the picture that emerges is one of gradual spatial unfolding. A supernova begins as an extremely compact collapse. It triggers a shock that propagates outward. It ejects material that expands for centuries. It creates remnants that span light years. And eventually, it dissolves into the background of the galaxy. At no point does the supernova suddenly become huge in the way explosions are depicted in fiction. Its growth is steady, governed by velocity and time rather than instantaneous expansion. The size we assign to it depends entirely on when we look and what we choose to measure. This makes the supernova a powerful example of why size in astrophysics is rarely absolute. Objects and events are better understood as evolving systems whose spatial extent is a function of process, not identity. The supernova is not a thing that grows large. It is an event whose consequences spread. By the time its remnants are large enough to be visually impressive on interstellar scales, the violence that created them is long over. What remains is motion, structure, and interaction, echoing the initial collapse that occurred on a scale far smaller than most people would ever guess. And through all of this, the original core, now a neutron star or black hole, remains compact, dense, and small, sitting quietly at the center or hidden entirely. The largest visible structures trace not the core itself, but the long aftermath of its brief, decisive collapse. So the size of a supernova is never a single answer. It is a history written in expanding space, shaped by time, and slowly erased as the universe absorbs the debris back into itself. As the expanding debris continues to move outward and interact with its surroundings, another shift happens in how size should be understood. The supernova is no longer defined by motion alone, but by influence. Its physical material keeps spreading, but its most important effects are no longer tied to where the gas currently is. They are tied to what that gas does to everything it encounters. The ejected material is rich in heavy elements forged during the star's life and death. Elements like oxygen, silicon, calcium, and iron are carried outward at enormous speeds. These atoms do not simply drift passively through space. They collide with interstellar gas, compress it, heat it, and change its chemistry. In many regions, this interaction triggers the collapse of nearby gas clouds, setting the stage for new stars to form. In this sense, the supernova's size expands far beyond the visible remnant because its influence reaches into regions that never directly touch the original debris. This is where the idea of a boundary becomes almost meaningless. The shock front marks a physical edge, but the effects extend beyond it. Radiation from the explosion can ionize gas light years away. Cosmic rays, accelerated by the shock, can travel even farther, threading through the galaxy and influencing magnetic fields and particle populations across vast distances. These particles move independently of the original expanding shell, carrying the supernova's signature long after the visible structure fades. At this stage, asking how big the supernova is becomes a question of definition rather than measurement. If size means where matter is, the answer is one thing. If size means where energy has traveled, the answer is much larger. If size means where conditions have been altered, the answer can be larger still. None of these definitions are wrong. They simply describe different aspects of the same event. This layered expansion highlights a fundamental truth about astrophysical phenomena. Physical extent and causal reach are not the same. The supernova's debris may occupy a region tens of light years across, but its influence can shape star formation, chemical evolution, and galactic dynamics on scales far beyond that. The explosion becomes part of the galaxy's long-term structure, even after its visible traces disappear. Over tens of thousands of years, the remnant slows and cools. The shock front weakens, the expanding shell fragments, and mixes with surrounding gas. Eventually, there is no longer a clear distinction between what came from the supernova and what was already present. At that point, the supernova no longer exists as an identifiable structure. Its material has become part of the interstellar medium, indistinguishable from other sources of gas and dust. Yet even here, the question of size does not vanish. Instead, it transforms. The supernova's contribution is now measured not spatially, but statistically. How much heavy material did it add to the galaxy? How much energy did it inject into the surrounding gas? How did it alter the balance between star formation and stability? These questions do not have spatial boundaries, but they define the supernova's lasting footprint. This is why supernovae are considered one of the primary engines of galactic evolution. A single explosion can influence regions far larger than its visible remnant, shaping the future of entire stellar neighborhoods. But again, this influence is not tied to the event being physically large. It is tied to the concentration of energy released in a brief time. Another complication arises when we consider different types of supernovae. Not all supernovae are created equal. Core collapse supernovae, which come from massive stars, behave differently from thermonuclear supernovae, which occur when a white dwarf accumulates too much mass. The latter involve stars that are much smaller to begin with, yet they can produce explosions of comparable brightness and energy. In a thermonuclear supernova, the star undergoing the explosion may be only slightly larger than Earth. The entire object is destroyed in a runaway nuclear reaction that consumes it in seconds. There is no compact remnant left behind. The initial scale is even smaller than in core collapse events, yet the outcome can still produce an expanding remnant spanning light years. This further emphasizes how misleading size can be if taken at face value. A star the size of Earth can produce an event whose aftermath stretches across interstellar space. Conversely, a star millions of kilometers across can collapse into something smaller than a city. The relationship between initial size, explosion mechanism, and final extent is anything but intuitive. It also explains why astronomers often avoid speaking about the size of a supernova without qualification. Instead, they describe velocities, energies, timescales, and interaction regions. These quantities capture the behavior of the event more accurately than any single spatial measurement ever could. When we observe distant supernovae, especially those in other galaxies, we do not see their size directly at all. What we detect is light. The light curve, the way brightness changes over time, contains information about the explosion's energy, the mass of ejected material, and how that material expands and cools. From this data, astronomers infer sizes indirectly, reconstructing the event rather than measuring it. This indirect nature of observation further disconnects size from perception. Two supernovae may look similar in brightness and duration while having very different physical extents at a given moment. Without detailed modeling, their apparent similarity can be deceptive. Even the term explosion can be misleading. In everyday language, an explosion implies a sudden outward blast with a clear edge and a defined volume. In astrophysics, a supernova is better understood as a rapid reconfiguration of matter and energy that initiates long-term expansion. The outward motion is real, but it is not the defining feature. The defining feature is the release of stored energy under extreme conditions. This distinction matters because it changes how we think about scale. A bomb explodes into empty space and creates a shockwave whose size can be measured relatively straightforwardly. A supernova explodes inside a star and then into a medium that is already structured, already dynamic, and already influenced by gravity, magnetic fields, and radiation. Its growth is shaped by everything it encounters. Over time, the expanding debris can become elongated, clumpy, or asymmetric. Some regions race ahead, others lag behind. The remnant becomes a complex three-dimensional structure rather than a simple sphere. Any attempt to assign a single radius becomes an approximation at best. The longer the supernova evolves, the less meaningful a single size becomes. Early on, size is tied to the star's structure. Later, it is tied to expansion, speed, and time. Eventually, it dissolves into influence without form. The supernova transitions from a physical event to a historical one. This is perhaps the most important insight when asking how big a supernova really is. The question assumes that size is the right lens. In reality, size is only briefly useful. Energy, time, and interaction tell the story far more faithfully. The supernova begins compact, becomes expansive, and ends diffuse. At no point does it settle into a stable, well-defined object with a fixed boundary. Its scale is always provisional, always dependent on context. The universe does not provide a single answer because the process itself does not have one. And yet, despite this ambiguity, the supernova remains one of the most consequential events in astrophysics. It creates the elements that make planets possible. It seeds galaxies with the raw materials of life. It sculpts interstellar space. None of these outcomes depend on the explosion being large in a spatial sense. They depend on it being intense, brief, and transformative. In the end, the size of a supernova is not something you can point to. It is something you trace through time. A collapse measured in kilometers initiates an expansion measured in light years, which then fades into a galactic influence measured not in distance but in change. That is why the question persists and why it resists a simple answer. A supernova is not big or small. It is scaled across time, unfolding from compact beginnings into widespread consequences, and leaving behind a legacy far larger than any snapshot of its physical extent could ever suggest. As the traces of the explosion continue to thin and merge into their surroundings, something subtle but important becomes clear. The supernova never truly stops. It simply changes the way it exists. The visible structures fade, the shock fronts weaken, and the once distinct remnant dissolves into the background of the galaxy. But the effects initiated by that brief collapse continue to propagate long after the last recognizable filament disappears. One of the longest-lasting consequences lies in the distribution of elements. Before the explosion, many heavy elements existed only inside the star, locked away from the wider galaxy. The supernova releases them into interstellar space, dispersing them over vast regions. Over millions of years, these atoms become part of new gas clouds, new stars, and eventually new planets. The calcium in bones, the iron in blood, and the silicon in rocks are all tied to supernovae that occurred long before the Sun formed. This means that the effective size of a supernova can be traced across time rather than space. The explosion affects regions that may never have been physically close to the original star, simply because galactic rotation, turbulence, and gravity redistribute material continuously. The elements from a single supernova can end up scattered across thousands of light years over cosmic timescales. There is no clear edge to this influence. It blends into the ongoing evolution of the galaxy itself. Energy, too, leaves a long imprint. The kinetic energy injected into interstellar gas stirs turbulence that can persist for millions of years. This turbulence regulates how gas clouds collapse, how stars form, and how efficiently galaxies convert gas into new stellar populations. Even after the shockwave has slowed to ordinary speeds, the motion it initiated continues to shape its environment. In this sense, the supernova's most expansive phase is also its quietest. There is no dramatic light show, no visible blast, no easily identifiable structure. Instead, there is gradual mixing, slow motion, and statistical influence. The event becomes diffuse not only spatially, but conceptually. It stops being something that can be pointed to and becomes something that must be inferred. This challenges the way size is normally understood. We are accustomed to thinking of size as something that can be drawn, outlined, or measured directly. But many of the most important astrophysical processes operate without clean boundaries. They act through redistribution, influence, and long-term change rather than through stable shapes. The supernova exemplifies this perfectly. At no point does it occupy a clearly defined, permanent volume. Its earliest phase is compact and violent. Its middle phase is expansive and luminous. Its later phase is diffuse and invisible. Each phase is real, yet none of them alone capture the whole event. This also reveals why supernovae are so difficult to classify neatly. Astronomers categorize them based on spectral features, light curves, and progenitor systems. But these categories describe behavior, not size. Two supernovae of the same type can produce remnants with very different appearances and extents depending on their environments. The surrounding density of gas, the presence of magnetic fields, and the history of nearby stellar activity all shape the outcome. In dense regions of a galaxy, a supernova's expansion may be slowed quickly, producing a compact remnant with complex structure. In sparse regions, the same explosion may expand more freely, spreading its influence over a larger volume before fading. The explosion itself has not changed. The context has. This dependence on environment further weakens the idea that a supernova has an intrinsic size. Its scale is relational. It depends on what surrounds it and how that environment responds. The supernova does not impose a fixed shape on space. It negotiates one over very long timescales. Even the concept of a remnant loses meaning As galactic processes continue, the enriched gas becomes fully mixed, the energy dissipates, the chemical signatures blend. At that point, there is no physical marker left that identifies the supernova as a discrete event. Its influence persists only as part of the galaxy's overall state. Yet even then, the supernova's legacy remains encoded in patterns that can be detected indirectly. The relative abundances of elements in stars carry information about the frequency and types of supernovae that occurred before them. The structure of galaxies reflects the cumulative energy input from countless explosions. The universe remembers supernovae statistically, even when it forgets them spatially. This statistical memory introduces a different way of thinking about scale. Instead of asking how big a supernova is, we can ask how much it matters. How much mass does it redistribute? How much energy does it inject? How much does it alter future evolution? These questions do not map cleanly onto distances or volumes, but they capture the true reach of the event. Seen this way, the supernova is both small and vast at the same time. It is small in the sense that it originates from a compact region and never dominates its galaxy spatially. It is vast in the sense that its consequences ripple outward through time, shaping structures far removed from the original star. This duality helps explain why supernovae occupy such a central role in astrophysics. They sit at the intersection of extremes: compact beginnings and expansive outcomes, brief durations and long-lasting effects, localized events and galactic-scale consequences. Their importance lies precisely in this imbalance. It also explains why attempts to visualize supernovae often fail to capture their essence. Images tend to focus on the most visually striking remnants, with glowing filaments and dramatic colors. These images are beautiful and informative, but they represent only a snapshot of a long story. They show where material happens to be at one moment, not the full scope of what the explosion has done. The deeper reality is less photogenic but more profound. A supernova reorganizes matter and energy in ways that cannot be fully captured in a single frame. Its true size is spread across time, influence, and probability rather than space alone. This perspective aligns with a broader pattern in astrophysics. Many of the most consequential processes do not correspond to stable objects. Star formation, galaxy mergers, and cosmic expansion are all processes rather than things. Their scales are not fixed because their identities are not fixed. They are defined by change. The supernova fits squarely into this category. It is not an object that grows large and then fades. It is a transformation that unfolds across multiple scales, leaving behind no single structure that can represent it fully. Its size cannot be pinned down because it does not exist at a single size. Understanding this requires letting go of the intuitive desire for a definitive number. There is no radius that captures a supernova in the same way a radius captures a planet. Any number we choose is a snapshot, useful for a specific purpose, but incomplete. What remains then is a layered understanding. The supernova begins with a collapse measured in kilometers. It produces ejecta that expand to light-year scales. It influences star formation and chemistry across regions far larger still. And finally, it dissolves into the background, leaving behind patterns rather than structures. Each layer is real. Each layer is measurable. None of them alone defines the supernova. Together they form a picture that is richer than any single measure of size could ever provide. By the time all visible traces have vanished, the supernova has become inseparable from the galaxy that absorbed it. Its atoms circulate. Its energy has long since dissipated. Its identity is gone. Yet its contribution remains embedded in everything that follows. This is the final irony of the question. The supernova that once briefly outshone an entire galaxy eventually becomes indistinguishable from that galaxy. The event that seemed impossibly dramatic ends quietly, not with a boundary or an edge, but with assimilation. So when we ask how big a supernova really is, the most honest answer is that it cannot be contained within a single scale. It is an event whose physical size grows, dissolves, and disappears, while its influence continues to spread long after its form is gone. Its true magnitude is not a matter of distance. It is a matter of transformation. When everything visible has finally thinned beyond recognition, when there is no longer a glowing shell, no clear shock front, and no distinct remnant to point at, the supernova has reached its most misunderstood phase. This is the phase where people assume it is over. In reality, this is the phase where its scale becomes hardest to see, not because it has vanished, but because it has become fully integrated into the systems around it. By this point, the material once ejected at thousands of kilometers per second has slowed to velocities comparable to the turbulent motion of the interstellar medium. The atoms are still there, but they no longer move as a coherent structure. They drift, collide, cool, and mix. The explosion has ceased to be an event and has become a condition. Nothing dramatic marks this transition. It happens gradually, invisibly, and without any clear moment of completion. This is where the idea of size dissolves completely. There is no longer a surface, no radius, no expanding boundary. The supernova does not occupy space in the way an object does. Instead, it contributes to space. Its atoms become part of clouds that may span hundreds or thousands of light years, but those clouds are not the supernova. They are new systems, shaped partly by what the supernova provided. At this stage, the most accurate way to talk about scale is through contribution rather than extent. How much of the surrounding gas carries elements that originated in the explosion? How much of the galaxy's current motion traces back to energy injected by long-dead stars? These are not spatial questions, they are statistical ones. Galaxies are not smooth, static structures. They are dynamic, turbulent systems, constantly reshaped by feedback. Supernovae are one of the dominant sources of that feedback. Over billions of years, countless explosions overlap in their effects, stirring gas, heating regions, and regulating how matter clumps. No single supernova controls a galaxy, but collectively they define its behavior. This collective influence introduces a different kind of scale, one that is often overlooked. A supernova's true reach cannot be understood in isolation. It must be seen as part of a population. Each explosion contributes a small increment of change, and those increments accumulate. The size of the effect emerges not from one event being large, but from many events being frequent. This is another reason the visual remnants can be misleading. They draw attention to individual explosions when the more important story lies in their overlap. The galaxy we observe today is shaped not by the largest or brightest supernova, but by the integrated effect of millions of them over time. Their combined energy input determines whether gas settles into disks, forms spiral arms, or escapes into intergalactic space. In this context, the size of a supernova becomes almost irrelevant compared to its timing. When explosions occur, matters more than how large their remnants grow. Bursts of supernova activity can shut down star formation in entire regions by heating and dispersing gas. Periods of quiet allow gas to cool and collapse again. The rhythm of explosions shapes the galaxy's evolution. From this perspective, a supernova is less like a bomb and more like a heartbeat. Each pulse is brief and localized, but the cumulative effect maintains the system's circulation. Remove supernovae from a galaxy, and its structure changes fundamentally. Gas collapses too efficiently. Star formation runs unchecked. The galaxy evolves along a different path, yet none of this requires a supernova to be spatially large at any given moment. Its importance comes from energy density and repetition, not sheer size. This again underscores how poorly suited simple spatial measurements are for capturing the essence of astrophysical events. The same principle applies on even larger scales. In galaxy clusters, the combined output of supernovae from many galaxies contributes to heating the intracluster medium. Heavy elements found between galaxies did not form there. They were ejected by supernovae and transported over enormous distances through gravitational interactions and galactic winds. The fingerprints of these explosions can be found far from where they occurred. At this level, asking how big a supernova is becomes almost absurd. Its atoms may now be spread across regions larger than the galaxy where the star originally lived. Its energy may have influenced environments that were never directly connected to the original system. The explosion's footprint is no longer bounded by any sensible spatial scale. And yet, despite this vast reach, the supernova remains fundamentally a small event in one crucial sense. It does not dominate the universe. It does not alter cosmic expansion. It does not reshape space-time on large scales. Its influence is profound but local, even when local spans thousands of light years. This balance between significance and limitation is essential. Supernovae are powerful enough to shape galaxies, but not powerful enough to disrupt the larger cosmic order. They operate in a narrow band of relevance, where they matter enormously without becoming globally overwhelming. This narrow band is where much of astrophysics lives. Stars, planets, and life itself exist in regimes where energy is concentrated enough to drive complexity, but not so concentrated that it erases structure entirely. Supernovae sit near the upper edge of this band. They are among the most energetic events associated with normal matter, yet they remain governed by the same physical laws that apply everywhere else. This is why their study is so revealing. They expose how scale works in the universe. They show how small beginnings can have wide consequences, how brief events can leave long-lasting imprints, and how size alone is rarely the decisive factor. By the time a supernova's material has fully mixed into the galactic environment, its identity has vanished. There is no label on an atom indicating which explosion created it. There is no boundary separating supernova matter from everything else. The universe does not preserve the memory of individual events, it preserves outcomes. Those outcomes include enriched gas, regulated star formation, and a dynamic balance between collapse and dispersion. None of these can be traced back to a single explosion without careful analysis. They are emergent properties of many overlapping processes. In this sense, the supernova's largest scale is also its most abstract. It exists as part of a statistical pattern rather than a physical structure. Its size is measured in influence rather than distance, in contribution rather than extent. This realization brings the original question into sharp focus. Asking how big a supernova is assumes that size is the defining attribute, but size is only briefly relevant and never complete. The supernova's true character lies in its ability to convert a compact collapse into widespread change. That change does not require a large object. It requires a release of energy under the right conditions. The universe responds not to size, but to imbalance. A supernova is an extreme imbalance, resolved rapidly with consequences that ripple outward through time. Once those ripples have faded into the background, nothing dramatic remains. No explosion, no glowing shell. just a slightly different universe than existed before. A universe with more heavy elements, more stirred gas, and a subtly altered trajectory. And that is the final form of the supernova. Not an expanding sphere, not a visible remnant, but a quiet alteration of what is possible next. It has no size because it no longer exists as a thing. It exists as history embedded in matter. The star that died is gone. The explosion has passed. The remnant has dissolved. But the universe that follows carries the imprint of that event in every generation of stars that forms afterward. So if size must be assigned at this stage, it is not a size that can be drawn. It is a size measured in consequence, a measure of how much the universe was changed by something that, at its most critical moment, was smaller than a city. That contrast is not a paradox, it is a lesson. In the universe, scale does not dictate importance. Timing, density, and transformation do. The supernova proves this better than almost anything else we observe. As the consequences of the explosion continue to diffuse through the galaxy, the supernova reaches a point where even its indirect influence begins to blur into the background of cosmic activity. At this level, its role is no longer dramatic or easily isolated. It becomes part of the universe's baseline behavior, indistinguishable from the countless other processes that shape large-scale structure. This is where the question of size gives way entirely to the question of persistence. Galaxies are not static archives that preserve individual events. They are dynamic systems in constant motion, continuously rearranging matter and energy. Gas clouds collapse, stars ignite, stellar winds blow material outward, and gravity redistributes everything again. Against this backdrop, the imprint of any single supernova fades, not because it was insignificant, but because the universe does not pause to remember. It integrates. This integration happens on timescales far longer than human history. Over tens to hundreds of millions of years, the atoms released by a supernova are carried along by galactic rotation, turbulence, and gravitational interactions. They may pass through multiple generations of stars, being incorporated into new stellar cores, expelled again through winds or later explosions, and recycled repeatedly. At this point, trying to assign a spatial size to the original supernova becomes meaningless. Its material is no longer localized. It has become itinerant. What remains traceable is not position, but composition. The chemical makeup of stars and gas clouds contains subtle clues about how many supernovae contributed to them and what types those explosions were. Ratios of elements reveal histories that span billions of years. From these patterns, astronomers reconstruct the cumulative activity of countless stellar deaths, not by locating their remnants, but by reading their chemical signatures. This approach underscores how profoundly the supernova's scale has transformed. It no longer exists as an expanding structure or even as a coherent influence region. It exists as a contribution to probability. It increases the likelihood that certain elements are present, that certain cooling pathways exist, that certain types of planets can form. Its effect is diffused into the conditions that shape everything that comes after. At this level, the supernova's size is better understood as a weighting factor in cosmic evolution rather than a physical dimension. It slightly tilts the balance of outcomes. Enough such tilts, repeated across time and space, steer galaxies toward particular evolutionary paths. Without supernovae, galaxies would look fundamentally different, but no single explosion dictates the outcome. This distinction matters because it reveals how the universe scales influence. Large effects do not require large structures. They require concentrated events whose consequences can be redistributed efficiently. Supernovae excel at this because they occur frequently enough, release energy intensely enough, and interact strongly enough with their surroundings to leave lasting marks without overwhelming the system. There is also a temporal aspect to this scale that is often overlooked. The supernova's most intense activity occurs over seconds to days. Its visible aftermath spans centuries. Its chemical and dynamical influence persists for millions of years. Its statistical imprint lasts as long as the galaxy itself. At each stage, the relevant scale shifts. Time stretches the event far beyond its original spatial boundaries. This stretching creates a kind of illusion. When we look at the universe today, we see the accumulated results of countless ancient supernovae layered on top of one another. Their individual identities are gone, but their collective influence defines the environment. The universe feels rich in structure and complexity precisely because so many small, intense events have been integrated over long periods. From this perspective, the supernova is not an isolated phenomenon, but a fundamental mechanism by which the universe explores its possibilities. It converts gravitational potential into motion, nuclear binding energy into radiation, and stellar interiors into galactic ingredients. It is a transition point between ordered systems and diffuse backgrounds. What makes this especially striking is how little space the supernova needs to initiate all of this. The decisive moment still occurs in a compact region deep inside a star. Everything that follows is a consequence of that brief, localized imbalance. The universe amplifies the result, not by making the event larger, but by letting its products circulate. This amplification, without enlargement, is a recurring pattern in cosmic evolution. Black holes, for example, can influence regions far larger than their physical size through gravity and radiation. Stars shape planetary systems despite being tiny compared to their orbital distances. Supernovae fit neatly into this pattern, demonstrating again that spatial size is rarely the best predictor of importance. As the supernova's contributions continue to blend into the galactic environment, they also become harder to separate from other sources. Stellar winds, cosmic rays, and galactic inflows all mix together. The universe does not label its inputs, it simply combines them. This makes retrospective analysis challenging, but it also highlights how the universe operates without bookkeeping. Eventually, the conditions created by many supernovae give rise to new stars that, in turn, may produce their own explosions. The process is self-sustaining, not because any single event dominates, but because the collective behavior maintains a balance between collapse and dispersal. Supernovae are both products of star formation and regulators of it. At this point, the notion of size has been fully replaced by the notion of role. The supernova's role is to redistribute, to energize, and to enrich. These functions do not require a persistent structure, they require a pulse. Once delivered, the universe carries on. This realization reframes how we should think about astrophysical extremes in general. The most impactful events are often those that briefly disrupt equilibrium, not those that occupy large volumes. The universe is sensitive to imbalance, not scale. A small region, driven far from equilibrium, can have consequences that propagate indefinitely. The supernova is a textbook example of this principle. It does not reshape the universe by becoming enormous. It reshapes it by injecting energy and material at the right moment and letting the universe do the rest. Gravity, motion, and time handle the expansion of influence. By the time all direct traces have vanished, the supernova's contribution has been absorbed so completely that it is no longer meaningful to speak of it as a distinct cause. It has become part of the background conditions from which new events emerge. The universe moves forward without reference to individual past explosions, even though it is fundamentally shaped by them. This quiet integration is easy to overlook because it lacks spectacle. There is no final flare, no last visible marker. The supernova does not announce its completion. It simply fades into irrelevance as a discrete event while remaining relevant as a contributor. And this brings the discussion of size full circle. The question began with an intuitive image of a massive explosion filling space. It ends with a realization that the most important scale of a supernova is not spatial at all. It is temporal and causal. It is measured in how long its effects persist and how deeply they are woven into future outcomes. The universe does not measure significance in kilometers or light years. It measures it in change. A supernova produces an extraordinary amount of change from an extraordinarily small beginning. Everything that follows is the universe responding to that change over time. In the end, the supernova's true size cannot be drawn, bounded, or directly observed. It exists as a chain of consequences that stretches from a collapsing core to the formation of future stars and planets. Its footprint is everywhere its material travels and everywhere its energy once flowed. That footprint has no edge. It fades gradually, merging into the countless other influences that shape the cosmos. The supernova becomes part of the universe's fabric, not as an object, but as a history embedded in matter and motion. So the final answer to how big a supernova really is lies not in any image or measurement, but in this realization: a supernova is as large as the future it helps create, and no larger than the moment it began. As this long chain of consequences settles into the background of cosmic activity, another subtle truth emerges. The supernova does not stand apart from the universe's normal behavior. It is not an exception. It is an extreme expression of rules that operate everywhere, all the time. Gravity collapses matter. Energy seeks equilibrium. Imbalances resolve themselves. The supernova simply compresses these principles into a brief, intense episode. This perspective removes some of the mystique without diminishing the significance. The supernova is extraordinary not because it breaks the laws of physics, but because it follows them so completely that their consequences become impossible to ignore. When a star collapses, there is no negotiation. The equations run to completion. The outcome is dramatic because the conditions are extreme, not because anything unusual is happening. Seen this way, the question of size becomes almost secondary. The universe does not distinguish between small and large in the way human intuition does. It distinguishes between stable and unstable, balanced and unbalanced. A supernova is an instability resolving itself. Its scale is determined by how far that resolution propagates before equilibrium is restored. This also explains why the universe is filled with structures that owe their existence indirectly to supernovae. Molecular clouds, star-forming regions, and even the distribution of galaxies all reflect a history of repeated energetic disturbances. Without these disturbances, matter would settle into simpler configurations. Complexity would be suppressed rather than encouraged. Yet complexity is not guaranteed. It is conditional. It arises when energy flows are strong enough to drive change, but not so strong that they erase structure entirely. Supernovae operate precisely in this narrow window. They are violent enough to reshape environments, but limited enough to leave something behind. This balance is fragile. Too few supernovae, and galaxies become overly efficient at forming stars, exhausting their gas quickly. Too many, and gas is blown out or heated beyond the point where it can collapse again. The universe does not tune this balance consciously. It emerges naturally from the statistics of star formation and death. Here again, scale is revealed as an outcome rather than a cause. The size of supernova remnants, the reach of their influence, and the persistence of their effects all arise from how often they occur and how they overlap. One explosion alone is not decisive. Many explosions, spaced appropriately in time and space, create the conditions we observe. This brings the discussion into a broader cosmic context. Supernovae are part of a feedback loop that governs the evolution of galaxies across billions of years. They regulate the conversion of gas into stars, distribute heavy elements, and inject turbulence into the interstellar medium. None of these roles depend on a supernova being big in the conventional sense. They depend on repetition, timing, and interaction. The universe, in this respect, behaves more like a fluid than a machine. Individual disturbances ripple outward, interact with others, and gradually dissipate. The pattern that emerges is statistical rather than deterministic. No single ripple defines the whole. The overall behavior emerges from the ensemble. This fluid-like behavior makes the notion of size particularly slippery. In a fluid, boundaries are temporary. Features form, evolve, and dissolve. The same is true of supernovae. Their remnants are transient structures, meaningful for a time and then absorbed into the background. The universe does not preserve sharp edges. As the remnants fade, the memory of the explosion shifts entirely into indirect evidence. Astronomers infer past supernova activity by studying element abundances, gas dynamics, and star formation histories. These clues do not point to specific locations or sizes. They point to frequencies, energies, and cumulative effects. This indirect memory is enough to reconstruct the broad outline of cosmic history. We know, for example, that the early universe contained fewer heavy elements and that successive generations of stars gradually enriched it. We know that galaxies with higher rates of star formation also experience higher rates of supernova explosions. We know that the balance between heating and cooling shapes galactic structure. All of this knowledge comes without ever needing to assign a definitive size to individual supernovae. The universe tells its story through patterns, not measurements of single events. This realization aligns with a deeper theme that runs through astrophysics. Many of the most important questions are not about how big or how far, but about how often, how intense, and how connected. Size is a convenient shorthand when dealing with stable objects. It becomes less useful when dealing with processes. A supernova is a process from beginning to end. It begins with a collapse, unfolds through expansion, and ends in integration. At no point does it settle into a stable form with a permanent boundary. Its identity is always provisional, defined by what it is doing rather than what it is. Understanding this helps clarify why popular depictions often miss the mark. They freeze the supernova at a visually striking moment and present that as the whole story. In reality, that moment is just one frame in a long sequence. The most important parts of the sequence are invisible, extended, and unremarkable when viewed in isolation. The true scale of a supernova is therefore not something that can be captured in a single image or number. It is something that unfolds across time and manifests through change. It is present in the composition of stars, the motion of gas, and the structure of galaxies long after the explosion itself has faded from view. This does not make the concept vague, it makes it richer. It forces us to adopt a more nuanced view of how the universe operates. Events are not defined solely by their immediate appearance. They are defined by their long-term consequences and their role in larger systems. From this perspective, the supernova's size is best understood as relational. It is large relative to the processes it disrupts and small relative to the systems it inhabits. It is neither trivial nor dominant. It sits at a scale where it can matter without overwhelming everything else. That scale is where much of the universe's interesting behavior occurs. It is the scale where energy flows can create complexity, where feedback loops can regulate growth, and where history can accumulate without erasing itself. Supernovae are key players in maintaining this balance. As the universe continues to evolve, new supernovae will occur, repeating the same fundamental pattern under different conditions. Each one will be unique in detail and identical in principle. Each will begin small, expand outward, and fade into integration. Each will add another layer to the statistical fabric of cosmic history. There is no final supernova that marks an endpoint. There is no ultimate size that defines them all. There is only an ongoing process of creation, disruption, and renewal, driven by the same physical laws that govern everything else. In this ongoing process, the supernova stands as a reminder that importance in the universe is not a function of size alone. It is a function of context, timing, and connection. A brief event in a compact region can reshape environments far beyond its immediate reach. That is why the question of how big a supernova really is leads us away from simple measurements and toward a deeper understanding of how the universe uses scale. It shows us that size is a tool, not a truth, and that the most meaningful scales are often the ones we cannot draw. What remains after all the expansion, all the fading, and all the integration is not a structure we can point to, but a universe that has been subtly, permanently altered. The supernova has done its work, not by becoming large, but by becoming consequential. And in that quiet aftermath, the universe continues on, shaped by countless such moments, each small in origin, each vast in effect, none defined by size alone. At this point, the question that quietly replaces all others is not how large a supernova becomes, but why the universe produces events like this at all. Once size has lost its authority as an explanation, what remains is function. The supernova exists because it resolves a problem that arises naturally in stellar evolution. Massive stars cannot remain stable forever. When they exhaust the processes that support them, collapse is unavoidable. The supernova is not an excess, it is a release. This reframing changes the emotional tone of the event. The explosion is no longer something that happens to the star. It is something that happens because of the star's internal history. The scale of the outcome is dictated not by spectacle but by necessity. The universe responds only as strongly as it must, and no more. This necessity-driven view explains why supernovae follow remarkably consistent energy scales despite enormous variation in progenitor stars. Whether a star is 8 times the mass of the Sun or several dozen times heavier, the energy released in the explosion falls within a relatively narrow range. This is not coincidence. It reflects the physics of gravitational collapse and nuclear matter. Once collapse begins, the available energy is set by the mass and structure of the core, not by the size of the star's outer layers. This consistency further undermines the idea that size governs outcome. 2 stars with very different radii can produce explosions with similar energies and similar long-term influence. The universe does not reward larger stars with proportionally larger explosions. It resolves collapse according to internal constraints. What makes this especially striking is how sharply the decisive moment contrasts with the extended aftermath. The core's collapse and rebound unfold in fractions of a second. The redistribution of material and energy unfolds over millions of years. The universe compresses cause and stretches effect. The temporal scale expands, even as the spatial boundaries dissolve. This compression and expansion reveal a deeper pattern. The universe often concentrates decisive change into brief moments, and then allows the consequences to diffuse gradually. Supernovae are not unique in this regard. Phase transitions in the early universe, star formation bursts, and even galaxy mergers follow similar logic. Sudden reconfiguration followed by long equilibration. Understanding this pattern helps clarify why the search for a supernova size is ultimately unsatisfying. Size captures neither the intensity of the trigger nor the duration of the consequences. It freezes a dynamic process into a static snapshot, and then asks that snapshot to carry meaning it was never designed to hold. The universe itself does not operate in snapshots. It operates in flows. Matter flows, energy flows, information flows. Supernovae redirect these flows abruptly, then fade into them. Their importance lies in redirection, not occupation. Another subtle insight emerges when considering what supernovae do not do. Despite their violence, they do not tear galaxies apart. They do not disrupt stellar orbits on large scales. They do not fracture space-time or alter cosmic expansion. Their reach is immense relative to stars, but modest relative to galaxies, and negligible relative to the universe as a whole. This restraint is not accidental. It reflects the hierarchical structure of the cosmos. Different scales are governed by different dominant processes. Supernovae operate powerfully at the scale of interstellar gas, but they are subordinate to gravity at galactic scales and irrelevant to cosmological dynamics. The universe compartmentalizes influence. This compartmentalization ensures stability. If every energetic event scaled upward without limit, structure could not persist. The fact that supernovae remain confined in their ultimate influence is what allows galaxies to survive repeated explosions without disintegrating. In this light, the supernova's size is not an error or a mystery. It is precisely tuned by physical law to matter where it should and to stop mattering where it should not. The explosion is powerful enough to enrich and regulate, but limited enough to preserve larger systems. This balance also explains why supernovae recur. They are not anomalies. They are integral components of a self-regulating system. Stars form, evolve, die, and return material to the environment in a way that sustains further star formation. The supernova is the mechanism that closes the loop for massive stars. From a broader perspective, the universe appears less like a place where large things dominate small ones, and more like a place where processes interact across scales without overwhelming one another. Supernovae sit at a junction point in this network, linking stellar interiors to galactic environments. The question of size dissolves completely when viewed this way. The supernova is not large or small. It is appropriately scaled. Its dimensions, energy, and duration are matched to its role. This realization invites a final shift in how we think about astronomical events. Instead of asking how big they are, we can ask what problem they solve, what imbalance do they correct, what transition do they enable. When framed this way, the supernova becomes intelligible without needing to be visually overwhelming. The collapse of a core resolves the problem of unsupported mass. The ejection of outer layers resolves the problem of trapped heavy elements. The injection of energy resolves the problem of runaway collapse in galactic gas. Each step is purposeful in a physical sense, even though no intention is involved. The universe does not design supernovae, it allows them. They arise naturally from the interaction of gravity, nuclear physics, and time. Their scale is a consequence of those interactions, not a goal. When the dust finally settles, literally and figuratively, what remains is not an expanding sphere or a fading glow, but a changed set of initial conditions for whatever comes next. New stars form from enriched gas, new planets condense from heavier elements, new systems emerge that would have been impossible without earlier explosions. This continuity across generations is where the supernova's true magnitude resides. It is not measured in kilometers or light years, but in lineage. It connects one era of the universe to the next. It carries information forward, encoded in matter. Every atom heavier than helium carries a history. Many of those histories pass through supernovae. In this way, the explosion's reach extends into every complex structure that follows, including those capable of asking questions about size in the first place. The universe does not preserve the memory of the event as an object, it preserves it as a condition. The supernova becomes part of the baseline from which new complexity arises. This is why the supernova, despite its dramatic imagery, is ultimately a quiet mechanism. Its loudest moment is brief, its longest effects are silent. It changes what is possible without announcing itself. Seen from this angle, the question of how big a supernova really is transforms into something more revealing. It becomes a question about how the universe manages change, how it concentrates energy without chaos, how it disperses consequences without losing structure, how it allows dramatic events to occur without destabilizing everything else. The answer is not found in size, it is found in balance. And that balance is the reason supernovae matter, not because they are large, but because they are precisely as large as they need to be. By the time all of these layers are taken together, a different picture of scale quietly settles in. The supernova stops looking like a single dramatic event and starts to resemble a hinge in the universe's long story. It is a turning point rather than a thing, a moment where one configuration gives way to another. Its significance lies not in how far it expands, but in how decisively it redirects what comes after. This redirection is subtle, because it does not announce itself with permanence. The universe does not preserve monuments to its own transformations. It allows them to pass, leaving only altered conditions behind. The supernova fits this pattern perfectly. Its most visible phase is fleeting. Its most important effects are long-lived and diffuse. This helps explain why the human instinct to ask for size feels so natural and yet so poorly matched to the phenomenon. Size is a way of fixing something in space, of making it graspable, but the supernova resists being fixed. It is inherently temporal. Its identity is spread across moments rather than locations. When viewed through this lens, the early collapse, the expanding debris, the fading remnant, and the eventual mixing into galactic gas are not separate stages of one object. They are different expressions of the same transformation as it unfolds under changing conditions. The universe is not creating a large thing and then erasing it. It is allowing a process to run its course. This is why there is no final, correct answer to how big a supernova really is. Any answer depends on where you choose to pause the process and what aspect you choose to emphasize. The core collapse emphasizes density and compactness. The expanding ejecta emphasizes motion. The remnant emphasizes structure. The chemical legacy emphasizes influence. Each is true and none is complete on its own. The temptation to privilege one of these perspectives usually comes from familiarity. Visual remnants feel real because we can see them. Numerical radii feel authoritative because they can be measured. But the universe itself does not privilege visibility or measurability. It privileges continuity. What matters is how one state leads into another. In that sense, the supernova's true scale is inseparable from time. It occupies a small region briefly and a large region indirectly. It acts intensely for a moment and subtly for ages. Its size, if the word must be used at all, is stretched across duration rather than distance. This way of thinking also dissolves the apparent contradiction between the supernova's violence and the universe's calmness. The explosion feels extreme because it compresses change into a short interval. But when spread out over the timescales on which galaxies evolve, that change becomes gentle. The universe absorbs it without strain. This absorption is not passive. It is active, mixing, redistribution, and rebalancing. The supernova injects energy, and the universe dissipates it. The supernova releases material, and the universe repurposes it. Nothing is wasted. Nothing is preserved as a relic. The result is a cosmos that appears both dynamic and stable. Stars explode, yet galaxies endure. Energy is released, yet structure persists. Supernovae contribute to this equilibrium by acting as release valves, preventing systems from locking into overly rigid configurations. Seen this way, the supernova scale is perfectly matched to its function. It is large enough to disrupt, but not large enough to dominate. It is intense enough to matter, but not intense enough to destroy the framework in which it occurs. This balance is not fine-tuned by design. It emerges naturally from the physics involved. Gravity, nuclear forces, and conservation laws constrain what is possible. The supernova sits at the intersection of these constraints, doing exactly what the equations allow and nothing more. This realization reframes awe. The supernova is not impressive because it is visually spectacular, though it often is. It is impressive because it reveals how the universe handles extremes without losing coherence. It shows how dramatic change can be integrated into an ongoing system. When we step back far enough, the explosion itself almost disappears. What remains is a pattern. Stars form, stars die, material circulates, complexity emerges. The supernova is one link in this chain. Remove it, and the chain changes. Include it, and the universe looks the way it does. At this level, the question of size has served its purpose. It has guided attention to the mismatch between appearance and importance. Once that mismatch is understood, size can be set aside. The phenomenon no longer needs to be framed spatially to be understood. The supernova becomes a lesson in scale literacy. It teaches that not all large effects come from large things, and not all large things produce lasting effects. It teaches that the universe operates through relationships rather than absolutes. This lesson extends far beyond stellar explosions. It applies to many of the most consequential processes in nature, from the formation of planets to the evolution of life. Small beginnings can have vast outcomes if they are embedded in the right context. Large displays can fade without consequence if they are isolated. The supernova embodies this principle in one of its purest forms. It is a moment where physics, time, and context align to produce a transformation that reshapes what comes next without leaving behind a permanent structure to mark its passing. In the end, the supernova does not need to be big in order to matter. It needs only to occur. Once it does, the universe takes care of the rest, spreading its influence quietly, steadily, and without regard for whether anyone is watching. And that is perhaps the most accurate way to understand its scale. The supernova is exactly as large as the universe allows it to be at each moment. No larger, no smaller. Its size is not fixed because its role is not fixed. It adapts, fades, and integrates, leaving behind a cosmos subtly but irreversibly changed. By the time the last trace of the explosion has vanished, the question of size has already answered itself. What mattered was never the boundary of the event, but the boundary it crossed, the transition from one state of the universe to another. Everything else is just measurement. When the last visible traces have faded, and even the indirect signatures have blended into the background, the supernova occupies a strange position in our understanding. It is no longer something we can point to, yet it remains something we must account for. Its existence is no longer spatial or visual, but logical. It explains why certain things are the way they are, even though nothing about it remains present. This is where the idea of size finally loses all practical meaning, not because the supernova was small or large, but because size is no longer the right language. What persists is a shift in conditions. The universe before the explosion and the universe after it are not the same, even if the difference is subtle and widely distributed. At this level, the supernova becomes comparable to a rule change rather than an object. It alters the initial parameters for future processes. Gas clouds collapse differently. Star formation proceeds with different efficiencies. Planetary systems form from richer material. None of this requires a spatial footprint that can be outlined or measured. It requires only that the conditions have been altered. This way of thinking reveals something important about how the universe encodes history. It does not preserve events as records. It preserves them as consequences. The past exists only insofar as it shapes the present. Once an event's effects are fully integrated, the event itself effectively disappears. Supernovae illustrate this more clearly than almost any other phenomenon. Their most dramatic phase is short-lived. Their most consequential phase is silent. The universe remembers them not as explosions, but as enriched matter, altered dynamics, and changed probabilities. This is why astronomers studying distant galaxies can infer the presence of past supernova activity without ever seeing a remnant. They read the chemical composition of stars. They analyze the motion of gas. They measure how efficiently galaxies convert gas into new stars. From these patterns, they reconstruct a history of stellar death that left no visible scars. The supernova's role in this history is precise. It is one of the few processes capable of redistributing heavy elements widely and rapidly. Without it, matter would remain locked inside stars until those stars quietly faded away. The universe would still exist, but it would be chemically poorer and structurally different. Yet even here, restraint is evident. Supernovae do not distribute matter evenly across the universe. They work within galaxies. Their reach does not extend into the voids between large-scale structures. Their influence is bounded not by distance, but by connectivity. They affect what they can interact with, and no more. This bounded influence reinforces the idea that the universe operates through nested scales. Processes matter most where they are connected. A supernova is deeply connected to its host galaxy and almost irrelevant beyond it. That does not make it insignificant. It makes it appropriately scoped. This nested structure is what allows complexity to persist. Each level of organization has processes that dominate within it and fade beyond it. Supernovae dominate at the scale of interstellar gas. Gravity dominates at the scale of galaxies. Cosmic expansion dominates at the largest scales. No single process overwhelms all others. Understanding this hierarchy helps dissolve the lingering intuition that size must correlate with importance. Importance is contextual. A supernova is immensely important within its domain and nearly irrelevant outside it. Both statements are true at the same time. This contextual importance also explains why supernovae are neither rare enough to be negligible nor common enough to be chaotic. They occur often enough to shape galaxies, but infrequently enough that their effects can dissipate before the next one arrives in the same region. The universe spaces them out. This spacing is not deliberate. It emerges from the statistics of star formation and stellar lifetimes. Massive stars live fast and die young. Lower mass stars live longer and die quietly. The distribution of stellar masses sets the rhythm of supernova activity. The rhythm, in turn, shapes the environment for future stars. At this point, the supernova's size has been fully reframed. It is no longer a question of how much space it occupies, but of how deeply it is woven into the universe's ongoing processes. The explosion is not a centerpiece, it is a thread. This reframing also clarifies why supernovae feel simultaneously dramatic and ordinary. Dramatic because they release enormous energy in a short time. Ordinary because they are a predictable outcome of stellar evolution. The universe expects them. It is built to absorb them. This expectation is built into the laws themselves. Nothing about a supernova requires special rules. Gravity collapses matter. Nuclear reactions release energy. Conservation laws govern the outcome. The scale of the event is an emergent property, not a fundamental one. When we strip away the imagery and focus on the mechanics, the supernova becomes almost modest. It does exactly what the equations say it should do. The awe comes not from violation, but from consistency across extreme conditions. This consistency is the quiet message behind the question of size. The universe does not become unstable when things get energetic. It does not lose coherence when structures collapse violently. It remains governed by the same principles at every scale. The supernova is a demonstration of this robustness. It pushes matter and energy to extremes, and the universe responds smoothly. There is no breakdown, no chaos spilling outward indefinitely. There is transformation, followed by integration. By the time all of this is appreciated, the original question has fully transformed. How big is a supernova? Becomes, what does a supernova do, and where does that matter? The answer is no longer a number, but a narrative of interaction. That narrative has a beginning, but no clear end. The explosion initiates a chain of consequences that merge into the universe's general behavior. The event dissolves, but the change remains. This is why supernovae are so central to our understanding of cosmic evolution. They are not endpoints. They are connectors. They link one generation of stars to the next. They bridge the interior of dying stars and the birthplaces of new ones. In the end, the supernova's scale is inseparable from its role. It is large enough to redistribute matter, small enough to preserve structure, brief enough to avoid domination, and persistent enough to matter. Its size is exactly what it needs to be for the universe to continue unfolding as it does. Once that is understood, the need to assign it a single dimension disappears. The supernova has done its work. The universe has moved on. And the question of size, having guided us to this realization, quietly falls away. By this point, the supernova has fully shifted from something that can be described into something that must be inferred. Nothing remains that announces its presence directly. There is no expanding shell to observe, no shock front to map, no glow to capture. And yet, the universe that follows is measurably different from the one that came before. This difference is not localized. It is woven into the conditions under which future structures emerge. What becomes clear here is that the universe does not store events the way memory does. It does not keep a record of what happened. It keeps only the outcomes. Once those outcomes are distributed widely enough, the event itself loses identity. This is not erasure, it is completion. In this sense, the supernova is an example of how physical processes conclude without leaving signatures that point back to them cleanly. The universe is not forensic. It does not preserve clues for later interpretation. It moves forward, continuously transforming past events into present conditions. This forward-only behavior makes size increasingly irrelevant as a concept. Size assumes a boundary. It assumes a region you can point to and say, this is where the event exists. But once the supernova's effects are fully integrated, there is no region left to isolate. The material has been mixed. The energy has dissipated. The structure has relaxed. What remains is indistinguishable from the background processes of the galaxy. At this level, the supernova's influence is no longer something added on top of the universe. It is something embedded within it. The explosion does not sit beside other processes. It becomes one of the reasons those processes behave the way they do. This embedding is why supernovae matter most when considered collectively. Individually, they are brief. Together, they define long-term trends. They regulate how galaxies age, how efficiently stars form, and how matter cycles between different states. The universe does not depend on any one explosion. It depends on the pattern they form over time. Patterns, unlike objects, do not have size in the usual sense. They have scale in a statistical sense. They describe how often something happens, how strongly it affects its surroundings, and how those effects accumulate. The supernova's final scale lives here, in statistics rather than geometry. This shift also clarifies why certain questions feel unanswerable. Asking how big a supernova is at this stage is like asking how big a rule is. The rule does not occupy space. It governs behavior. Supernovae act like rules injected into the system temporarily, altering trajectories before dissolving back into the background. The universe is full of such temporary rules. Star formation thresholds, cooling rates, and feedback mechanisms all arise from physical conditions that persist for a time and then fade. Supernovae are among the most influential of these, not because they last long, but because they occur at critical moments. This emphasis on timing over size is crucial. A supernova that occurs in a dense, star-forming region can have a very different impact from one that occurs in isolation, even if both release similar amounts of energy. The surrounding environment determines how effectively the explosion's energy and material. Again, scale emerges as relational rather than absolute. The same event can feel large or small depending on context. The universe does not assign a fixed importance to events. Importance emerges from interaction. At this depth, it becomes clear that the original intuition behind the question of size comes from a human desire for containment. We want to draw boundaries. We want to know where something begins and ends. The universe does not operate this way. Processes overlap. Influences blend. Boundaries are provisional. The supernova challenges containment more forcefully than most phenomena. It begins deep inside a star, escapes into space, reshapes its surroundings, and then disappears into the very medium it altered. There is no moment when it can be fully enclosed within a definition. This is not a failure of language or measurement. It is a reflection of how dynamic systems behave. They do not have fixed extents, they have trajectories. The supernova's trajectory runs from compact collapse to diffuse integration, crossing many scales without ever settling. Understanding this helps resolve the tension between spectacle and subtlety. The explosion is spectacular because it concentrates change. The aftermath is subtle because that change is distributed. Both are part of the same process. What remains at the end is not a supernova-shaped region of space, but a universe slightly altered in composition, motion, and potential. New stars will form from enriched gas. New planetary systems will inherit heavier elements. New structures will emerge that would not have been possible otherwise. The supernova does not need to remain visible to matter. It needs only to have happened. Once it has, the universe incorporates its outcome and moves on. The event becomes history, and history becomes condition. This is why, in the deepest sense, the size of a supernova cannot be separated from the question of relevance. Its relevance persists long after its size has become undefined. The two do not track together. One fades while the other remains. By now, the initial question has done its work. It has led from intuitive images of explosion and expansion to a more nuanced understanding of how physical processes scale. It has revealed that the most important dimensions of an event are often the least visible ones. The supernova, stripped of imagery, stands as a reminder that the universe is shaped less by objects than by transitions. What matters is not how much space something occupies, but how it alters the flow of matter and energy. Once that alteration is complete, the universe does not look back. It does not preserve the event as a separate entity. It continues forward, carrying the consequences quietly. At this point, the supernova has fully disappeared as an event, even though its influence remains everywhere it mattered. The question of size has lost all traction, not because it was wrong to ask, but because it has been answered as far as it can be. What remains is a universe that has been changed, slightly but irreversibly, by something that no longer exists as a thing. And that is, perhaps, the most accurate way to understand not only supernovae, but many of the processes that shape reality. They do not endure as structures, they endure as conditions. At the very end of this reasoning, the supernova leaves behind something more subtle than matter, energy, or motion. It leaves behind constraints. The universe after a supernova is not free to evolve in the same way it would have without that event. Certain possibilities have been opened, others quietly closed. This is the final and most elusive sense in which a supernova has scale. Before the explosion, the future of the surrounding region is limited by what the star has not yet released. Heavy elements are locked away. Energy is confined. The surrounding gas follows one set of pathways. After the explosion, those pathways multiply. Cooling becomes easier because metals radiate heat efficiently. Dust grains can form. Molecular clouds can collapse in ways that were previously forbidden. Planets can acquire compositions that were once impossible. These changes are not dramatic in isolation. They do not announce themselves with light or motion. They are changes in what is allowed to happen next. This is where the supernova's final scale resides, not in distance, but in possibility space. Once a supernova has occurred, the universe around it has more options available. Chemistry becomes richer. Structure formation becomes more varied. Complexity gains footholds that were absent before. None of this requires the supernova to occupy space anymore. The event has already done its work by reshaping the rules under which future processes operate. This idea challenges one of the deepest intuitions about physical size. We tend to assume that the reach of an event ends where its material ends. The supernova shows that this assumption is wrong. Its reach extends wherever the constraints it altered still apply. Those constraints can persist long after the material has mixed beyond recognition. At this level, the supernova no longer belongs to astronomy alone. It belongs to the logic of systems. It demonstrates how a brief, localized disturbance can permanently reshape the landscape of outcomes. The universe does not need to remember the event. It only needs to carry forward the conditions it created. This perspective also clarifies why the universe does not appear chaotic despite being shaped by violent events. Supernovae inject energy, but they also enable dissipation. They create disorder locally, but they enable higher-order organization globally. The apparent contradiction dissolves once size is replaced with role. The universe is not a place where explosions simply add noise. It is a place where certain kinds of disruptions are essential for progress. Without supernovae, galaxies would stagnate. Matter would remain locked in simple configurations. The pathways leading to planets, chemistry, and life would be sharply constrained. Yet supernovae do not overwhelm the universe with excess possibility. They do not open every door at once. They expand the space of outcomes just enough to allow complexity to grow without losing coherence. This moderation is not intentional. It is a consequence of how energy scales, how matter interacts, and how time allows redistribution. Here, the concept of size has fully transformed. It no longer refers to extent or expansion. It refers to impact on the future. The supernova is large because it enlarges what the universe can do next. It is small because it does so without dominating everything else. This reframing also explains why supernovae feel foundational when we trace the origins of complex structures. They are not the only source of change, but they are among the most decisive. They act as gateways between simple and complex states, between early and later eras of cosmic evolution. Once those gateways are crossed, the universe does not keep track of how they were opened. It simply moves forward through them. The star that collapsed is gone. The explosion is over. The remnant has dissolved. What remains is a universe that can no longer return to its previous state. This irreversibility is the final measure of scale. An event is large if it cannot be undone. In this sense, every supernova is enormous. It permanently alters the distribution of matter and energy in ways that no future process can completely reverse. The universe absorbs the change, but it does not erase it. This does not mean the universe accumulates history in a visible way. It means that history accumulates in constraints. Each supernova slightly reshapes the terrain on which future events unfold. Over time, these small reshaping events build the complex cosmos we observe. By now, the original question has transformed completely. How big is a supernova? Began as a spatial curiosity. It ends as a question about how deeply an event is woven into what comes after. Size, in the conventional sense, has been left behind. What remains is a recognition that the universe is structured less by enduring objects than by irreversible transitions. Stars form, stars die, explosions occur, and matter circulates. The identity of each event fades, but its contribution remains embedded in the flow. The supernova is one of the clearest demonstrations of this principle. It shows how something can be momentary yet decisive, localized yet far-reaching, violent yet constructive. Its scale cannot be captured by a snapshot because it exists across time, influence, and possibility. In the end, the most honest way to describe the size of a supernova is to say that it is exactly as large as the change it introduces, and no larger. It does not fill space. It fills the future with options that did not exist before. Once those options are in place, the universe no longer needs the event itself. It has already been transformed. The supernova has completed its role, not by persisting, but by disappearing. And in that disappearance, its true magnitude becomes clear. At this stage, the supernova can no longer be described as something that happens. It has become something that has happened, and that shift matters. Events exist only while they are unfolding. Once they are complete, what remains is not the event itself, but the altered landscape it leaves behind. The universe moves forward, carrying that landscape as its new baseline. This is where the supernova's final form becomes clear. It is not an object, not a structure, not even a process anymore. It is a condition embedded in the universe's present state. The universe after a supernova is subtly constrained and enabled in ways the universe before it was not. These constraints are invisible, but they are decisive. Cooling rates in gas clouds change. Fragmentation patterns shift. The minimum mass for certain kinds of stars is altered. Dust grains can exist where none could before. Chemical pathways that were previously inaccessible become common. None of these outcomes require the supernova to still occupy space. They require only that its influence has been absorbed. This absorption is irreversible. Once heavy elements are released and mixed, there is no mechanism that gathers them back into the original star or restores the earlier simplicity. The universe does not rewind. It accumulates complexity by losing the option to return to simpler states. Each supernova contributes to that accumulation. Here, scale is no longer something that spreads outward. It is something that locks in. The supernova's reach is defined by how deeply its consequences are embedded into future evolution. The deeper the embedding, the larger the event in this final sense. This reveals a powerful inversion of intuition. Early on, the supernova feels largest when it is brightest and fastest, when material is flying outward and shockwaves are visible. In reality, this is when its influence is most temporary. The lasting scale emerges later, when everything has slowed down and settled into new rules. The universe values persistence over spectacle. A brief flash of energy matters less than a slight, permanent shift in how matter behaves afterward. Supernovae excel at producing those shifts. They alter ratios, thresholds, and probabilities in ways that cannot be undone. This is why their importance grows with time rather than shrinking. The longer after the explosion you look, the more systems have incorporated its consequences. New stars form differently. New planets assemble from richer material. New environments appear that never could have existed before. The supernova's scale therefore increases, even as its identity vanishes. This is not a contradiction. It is a reminder that influence does not require presence. Once a change is encoded into the conditions of a system, the system carries it forward automatically. At this point, the question of size has become almost philosophical. We are no longer asking about meters or light years. We are asking how much of the future depends on something that no longer exists. And the answer is more than intuition suggests. The universe we observe today is layered with the consequences of countless past supernovae. Their individual stories are lost, but their collective impact defines the environment in which everything else unfolds. Remove them from history, and the universe would not resemble the one we know. This layered accumulation also explains why the universe appears directional in time. Complexity increases not because the universe aims for it, but because irreversible events like supernovae continually eliminate simpler configurations. Each explosion removes options while creating new ones, pushing the system forward into states that cannot be retraced. The supernova, then, is not just an explosion, it is a ratchet. It allows motion in one direction only. Once it has occurred, the universe cannot return to its previous chemical or structural simplicity. Time has advanced in a way that cannot be undone. This irreversible contribution is the final measure of scale. An event is large if it permanently shapes what comes after. By that definition, every supernova is enormous, regardless of how briefly it shines or how far its debris travels. The paradox resolves itself here. The supernova does not need to remain visible to remain important. It does not need to occupy space to define the future. Its work is done once the constraints it created are in place. The universe does not memorialize this work. It does not mark where the explosion occurred or preserve a record of when it happened. It simply proceeds under the new conditions, indifferent to their origin. This indifference is not neglect. It is efficiency. The universe does not waste effort maintaining identities that no longer serve a function. Once an event has altered the rules, the event itself is obsolete. And yet, from within the universe, from the perspective of systems that arise later, those obsolete events are foundational. Everything complex is downstream of them. Every atom heavier than helium, every planet with a rocky surface, every chemistry-rich environment traces back through countless supernovae. At this depth, the idea of measuring a supernova's size feels almost misplaced. What we are really measuring is how much of reality is downstream of it. The answer is not something that can be captured in a diagram. The supernova's final scale is therefore not spatial, temporal, or energetic. It is causal. It occupies the future by shaping the conditions under which that future unfolds. Once that is understood, the question that started this exploration no longer needs a numerical answer. The universe has already answered it through what it became. The supernova is as large as the difference between a universe without heavy elements and one with them, as large as the difference between sterile gas clouds and star-forming regions, as large as the difference between a cosmos of light elements and one capable of complexity. Does not look large anymore, but it does not need to. Its size is already written into everything that followed. At the very end of this long chain of reasoning, what remains is not an explosion, not a remnant, and not even a clearly identifiable influence. What remains is a realization about how the universe treats events once they have finished doing their work. The supernova does not persist as a monument. It persists as a condition that no longer needs explanation. This is the quiet resolution of the question that started everything. The universe does not care how big a supernova once was. It cares only that it happened. Once the consequences are absorbed, the event itself becomes irrelevant to ongoing dynamics. There is no lingering emphasis, no special status preserved in space or time. The universe moves forward under new constraints without acknowledging where they came from. This tells us something fundamental about how reality operates. Events do not matter because they are dramatic. They matter because they change what is possible next. Once that change has been made, the universe no longer needs the event. It has already been transformed. In this final sense, the supernova is neither large nor small. It is complete. Completion is not disappearance, and it is not destruction. It is the point at which an event has fully merged into the fabric of reality. Nothing remains that requires continued reference to the cause. The star that collapsed is gone. The explosion has faded. The remnant has dissolved. The shockwaves have softened. The atoms have mixed. The energy has thermalized. There is no trace left that demands attention. And yet, the universe that exists afterward is fundamentally different from the one that existed before. That difference is subtle, but it is everywhere. It is present in the way gas cools, in the way clouds fragment, in the way stars ignite, in the way planets form, in the way chemistry unfolds. These are not dramatic signatures. They are baseline behaviors. They define the normal operation of the cosmos. This is the final answer to the question of scale. The true scale of a supernova is not how far its debris traveled, how bright it once was, or how violently it exploded. Its true scale is how deeply it altered the rules under which everything else proceeds. The universe does not preserve memory, it preserves structure. Once structure has been altered, memory is unnecessary. The supernova story ends the moment the universe no longer needs to remember it. From a human perspective, this feels unsatisfying. We are drawn to events that leave visible traces, to things we can point to and say, this is where it happened. But the universe does not operate on narrative logic. It operates on physical logic, causes matter only until their effects are established. This is why the supernova, despite its violence, ultimately leaves behind no signature of importance. Importance is measured forward, not backward. What matters is not where the explosion was, but what came from it. In this way, the supernova becomes a perfect example of how the universe handles change. It allows dramatic transitions to occur, integrates their consequences, and then continues as if nothing special happened, because, from the universe's perspective, nothing did. It was simply another resolution of imbalance. There is something deeply instructive in this. It shows that permanence is not required for significance. A moment can reshape eternity without leaving behind a marker. A brief collapse can define billions of years of future behavior. The universe does not need to hold on to the cause to carry the effect. At the end of everything visible, the supernova has fully vanished as an event, but the universe is now richer, more complex, and more constrained than it was before. That is the only measure that remains. If we insist on one final way to describe its size, it would be this. The supernova is as large as the difference between what the universe could do before it happened and what the universe can do afterward. That difference cannot be drawn, it cannot be photographed, it cannot be measured in distance or duration. It exists only in outcomes. And once those outcomes exist, the event itself is no longer needed. The universe continues, not carrying the supernova with it, but carrying what the supernova made possible. Nothing explodes anymore. Nothing glows. Nothing expands. There is only a universe quietly behaving differently than it once did. That is the true end of the supernova, not a fading light, not a cooling shell, but a completed transformation. And in that sense, the question of size finally dissolves, not because it was meaningless, but because it has been answered as far as reality allows. What remains is not an explosion. What remains is the universe, slightly changed forever.